All right. So I know I kept saying that your test is Friday. It's actually Monday, which I hate putting tests on Monday, but that's just the way it has to be this time. I'm sorry. Okay, so this is 27.2 matter waves. We're going to talk about why light is both particle-like and wave-like. We'll calculate de Broglie's wavelength, and we'll calculate the momentum of a photon. So let's talk about Louis de Broglie. Or de Broglie, or, probably some sort of French name. In 1923, he proposed that particles could have wave-like properties. So Planck produced, the Planck constant with the equations that said that waves have particle-like properties. So this is the opposite. De Broglie was looking at particles and saying they had wave-like properties. So between the two of them, and Einstein kind of helping them along, they were able to unite this wave-to-particle and particle-to-wave theory and come up with the electromagnetic theory. So at the time, remember that scientists were very much on either the wave side or the particle side. So between Planck and de Broglie, they were able to unite. And by 1927, everyone pretty much said, okay, they're united. So here's the equation that he came up with. He gave waves momentum, which is really strange, because how can you have momentum, which is mass times velocity, right, for a wave which doesn't have any mass, like a photon? See, a photon doesn't have any mass. So how can it have momentum? But, and I'll come back to this, photons interact with electrons from the Compton effect, with the electron and the photon scattering. They're affecting it, and the photoelectric effect, right? The light, the photons causing electrons to move on. So this is momentum, right? It's a collision. So how can this photon interact with the electron if it doesn't have any mass? So what he did is he said, okay, a wavelength is equal to Planck's constant over momentum. And I broke down momentum here for you and v. So this is known as the de Broglie wavelength. He said that all particles have a wavelength. They're wave-like. They have a wave property. And they call that the de Broglie wave. And just in case you're wondering, this lecture is much, much shorter than yesterday. So you struggled yesterday. Don't worry. So remember that he proposed this in 1923. By 1927, everybody pretty much said, yep, that's the thing. We agree. So it didn't take long for the two sides to unite. They did lots of experiments to figure out that interference they had electrons, which are particles, right, could undergo interference and diffraction, which are wave properties. So this here was evidence to support particles with wave properties. And we don't really notice this in everyday life because the wavelengths for our masses are really, really small. So, think about a bowling ball, like a 2 or 3 kilogram bowling ball or something. That bowling ball has a wavelength that's like nanometers wide. It's tiny. So your bowling ball doesn't really look like it's, a wave because it's vibrating so small. But if you look at an electron is already really small, and its wavelength is going to be bigger than it. And we'll do a couple of calculations, and you can see that for an electron, it does make a big difference. But for a bowling ball, it doesn't. Because the bigger the mass, the smaller the wavelength. Whereas with an electron, compared to the size of an electron, the wavelength is actually much bigger. So, is light a particle or is it a wave? Between Planck and de Broglie, they have pretty much decided that light is like a hybrid of the two. It is its own thing. It has wave-like properties and it has particle-like properties. So since it has properties of both, it has a dual nature, which leads us to quantum mechanics. This is what quantum mechanics is all based on, is this properties of particles and lights trying to be merged together. It has a percentage chance of, a probability of acting like a particle or acting like a light. And by looking at one thing, you're forcing it to either act like a wave or act like a particle. Because it has this chance, this probability, this kind of leads into multiple timelines, multiple dimensions, so on and so forth. Some of that string theory stuff that you've heard about, some of the crazier things, that is pretty much related to quantum mechanics, and it's where it came from, because the physics actually supports it. All right, and then we have the Heisenberg uncertainty principle, which I'm sure you've heard of, even if you're not quite sure what it means. It says that we cannot know the exact position and momentum of a particle at a single time. So if you know exactly where that particle is, you will not know how fast it's going. If you know exactly how fast it's going, you will not know where it is. You can measure one or the other. You can't measure both at the same time with exactness. That's where your probability areas come into effect. So if you remember from chemistry, you have like your s orbital, and you have your p orbital, and another p orbital, and some sort of p orbital like that. They're areas of probability where that electron can be. So we don't know exactly where it is. We know it's going to be somewhere in that general area. There's a high percentage chance of finding it in there. Because if we knew exactly where it was, we'd have no idea how fast it's going. So if you know kind of where it is, you can kind of know how fast it is. It's the degree of exactness that you can measure. So there's a limit. Okay, you guys ready for the practice? I told you it was pretty short. Here we go. De Broglie's wavelength. What is the de Broglie wavelength for an electron traveling at the speed of light? Notice there's no actual numbers in here. All the numbers are going to be constants for this one. So let's look at these. We got one equation that we're working with today, and that is wavelength equals h over momentum, which is mass times velocity. So wavelengths, so waves can have momentum too. And in this it says, what's the de Broglie wavelength? So we're looking for lambda. H is 6.63 times 10 to the negative 34. This is Planck's constant. It's joules per hertz. Watch out for your units in this one. It says an electron is traveling at the speed of light. So we have the speed of light, which is c. This is your velocity. 3 times 10 to 8 meters per second. And it's an electron, so the only other thing we have is mass. So you want to look in the back of your book for the mass of an electron, which I do believe is 9.1 times 10 to the negative 34, but I could be wrong, so you might want to double check that one. 31. Oh, I said 34. I said 31, but I actually wrote 34. Thank you. Okay. So now we just plug it in. Wavelength equals Planck's constant over the mass and the speed of light. .43 times 10 to the negative 12, and this will be in meters. Now, if you want to get really fancy, again, you can just leave it like that, but if you want to get fancy, negative 12 is picometers, so it's 2.43 picometers. Again, you don't have to put that, it's just a little fancy thing. Easy peasy, right? Okay, let's do a hard one. This one says, what is the de Broglie wavelength of an electron that's accelerated by a 100-volt potential difference? So we've got to pull up some equations from yesterday. Hello? Okay. Becky, Dean's office. Dean's office. Ruby called for you. Okay, so got the de Broglie wavelength of an electron accelerated by 100 volt potential difference. Yesterday, you guys remember the equation that had the voltage in it? What was it? KE, kinetic energy, equals negative the charge of an electron times the voltage. What else was kinetic energy equal to? Good, 1/2 mv squared. So, we know the mass of an electron, Planck constant. We don't know velocity, but we do know voltage. So we're going to solve for velocity using voltage and charge. The charge of an electron is constant. Then we'll take the velocity and plug it in here and solve. That's the hardest type of problem you can be given today. So let's do that. We have 1/2 mass of an electron. Velocity is what we're looking for. Negative the charge of an electron. And then this potential of 100. All right, there's our velocity. And now that we have our velocity, we can plug it into this equation and solve for the wavelength. So wavelength is going to be Planck's constant over the mass of an electron times that velocity that we just found. Again, you can leave it like that, that's fine. I just put it here so we can look at the difference. 2.43 versus 12.3. So changing its velocity has a huge effect. Look at the size of these things. Now, electrons are really, really, really tiny. Tiny, tiny, tiny. And look at the wavelength size of this. Negative 12 picometers. Atoms are so much smaller than that. Electrons are so much smaller than that. So this affects an electron a lot. Whereas your bowling ball only is affected by like nanometers. So it doesn't really look or act like a wave because its wave-like properties are tiny. All right, I have 4 clicker questions for you today. Here's the first one. Why is the wave nature of objects we see and handle every day not observable?